what I'd like to do now is I'd like to turn to the primary focus of Section 4, which is parameterizing the quantile parameters with other parameters, and that can be useful in a lot of different ways that you might not have thought of, and initially we didn't think of these things either. I'm first going to talk a little bit about the sum of lognormal distributions. Now, as you may know, those of you that have a statistics background, efforts to sum lognormal distributions date back more than a century. And nobody has succeeded until now. Basically, you can see this quote from the literature. 2008, one of the most surprising facts about elementary probability theory is that almost nothing is known about the sum of lognormals. Normal distributions you can sum and get another normal distribution if they're identically distributed. Log-normal distributions you can sum. If you have an infinite number of them, then you will, by the central limit theorem, you get a normal distribution. But if you want to sum 2 or 3 or 5 identically distributed log-normal distributions, there's no closed form equation to that. And people have been trying to solve this for more than a century. And it's an important thing also. The sum of correlated or even independent log-normal random variables, wide interest in wireless telecommunications. It remains unsolved despite long-standing efforts, and this is another 2008 paper. In actuarial science, this is one of the most tangible ways you can think about why you'd want to sum lognormals. Individual claims for an insurance company, you can think you've got a policy that covers such and such, whatever it is. Individual claims are often well represented by a lognormal distribution. Can't be less than 0. It has a long tail. Each individual claim submitted to an insurance company on a particular policy, a policy of particular design, has its own characteristic lognormal distribution. And if you're running an insurance company, you need to be able to budget and you need to be able to price those policies. And in order to be able to do that, you have to add together, in effect, what's the sum, first of all, how many claims am I going to have in a given year? Let's say it's 100, okay? And then what's the probability distribution? Then what is the probability distribution over the sum of 100 such claims? I mean, it's a very, very clear problem, but it's actually very hard to simulate because, as Sam pointed out to me when we got into this, you first have to do a simulation on, for example, a Poisson distribution over the number of claims, and then conditional on whatever your Poisson distribution came up with, you then need to do another simulation inside a simulation, summing up all these log-normal distributions, which makes for a very, very awkward and computationally intensive process. Sam came to me a couple of years ago and said, could we do this in closed form? And at the beginning, I thought probably not, but pretty soon we had figured out a way to do it. So as background here, and you've seen a chart like this before, what this chart illustrates is that if you take 9 quantiles, these exact quantiles shown right here, and let me get my pointer going here, these quantiles right here off of a log-normal distribution. So if you take, for this case, sigma equals 0.3, that's one parameter of a log-normal distribution. The other parameter, mu, is 0. That distribution has an exact set of quantiles right here. Now this y vector, my cumulative probability y, I call that a reference probability vector. I could pick any set of quantiles I wanted to. I just picked a relatively symmetric step that gives some reasonable attention to both the tail, all the way from the tails all the way up to the 0.99. And what are the x's that correspond to that? That's this data. If you parameterize a log-metalog distribution with that, you get this this thin yellow line here. And if you contrast that with the exact log-normal distribution that underlies that, you cannot distinguish between the two. So, and we've seen this in multiple other applications, particularly in session 1, where we showed that the metalog can fit virtually any smooth continuous distribution so closely that you cannot distinguish between that distribution and the metalog representation of it. Now, why is this important? Because this is for a single log-normal distribution. I haven't done any adding of them together yet. Well, for a single log-normal distribution, this is relatively trivial because we know the quantile parameters, right? But what about for the sum of two identically distributed log normal distributions, or the sum of 5? Well, you don't know those quantile parameters. What do you do then? Well, the most sensible thing to do at that point is to probably do a simulation, because if you say I've got 20 log normal distributions that I wish to add together, my mu is 0, my sigma is 1.382, well, that's a very well-defined probability distribution in the sense that you could simulate the heck out of it, and you could come up with the quantiles of the resulting simulation. And in this case, what we did is we simulated it 50 million times, so that your random number seed basically makes no difference. You change your random number seed, you're going to get exactly this histogram that's shown, okay? So the sum of log normals is a very well-defined probability distribution. It just doesn't have any closed form representation. That's the issue that people have been having for 100 years. Well, let's take a look at, there have been probably 20 or 30 papers in the literature published as people attempt to approximate the sum of log normal distributions with some closed form representation. So a number of these papers, such as this one from 2009, attempt to represent the sum of log normal distributions with a log normal distribution, which sort of makes sense because the log normal, it still has, the sum will still have a lower bound of 0 and it'll still have a long tail. But this method is doomed to failure because the sum of log normal distributions inherently has a shorter tail than the log normal distribution that was the thing that was being summed across. So it's never going to work, but people have written papers on it thinking, well, maybe that's the best we can do. The gold standard, up to a year or two ago, was this Bolio and Rajwani 2004 paper, where they came up with a pretty reasonable closed form equation for the sum of log normals as a function of the number of log normals being summed and the sigma parameter. The mu parameter, by the way, is a scale parameter, so it doesn't really matter. But sigma and the number make a big difference. So the question is, if you do your 50 million simulations, what would and then you took 9 quantiles off of that corresponding to your reference probability vector, which is quite a straightforward thing to do, and then you fit a log metalog to that, what would it look like? And the answer is, here it is. And as you can see, the log metalog is virtually indistinguishable from the 50 million simulation histogram. Let me show it to you again. There is without it, and the gold standard is that orange curve. Well, we now have a new gold standard, which is the log metalog representation of the sum of log normals. And it's virtually exact. You can't see the difference. Now you might say, well, wait a minute, is that just for this one particular n of 20 and this one particular sigma of 1.382? And the answer is no. Here are a whole bunch of different sigmas and a bunch of different n's, and in each case you can see the 50 million simulation histogram and the log normal fit to that and the log metalog fit to that histogram, which is virtually indistinguishable. So now we have a new method of representing the sum of log normals. The log metalog can represent in closed form a well-defined probability distribution that otherwise has no closed form representation. So here's exactly what we've done. We did our 50 million simulations, and on each one of those, for each of a wide range of n, okay, in this particular example, and we took off of those simulations, each simulation we took off 9 quantiles, and we used those quantiles to pass a log metalog distribution to pass through those quantiles. And of course, if you're using a 9-term log metalog and 9 quantiles, it'll go through every one of those quantiles exactly. So there cannot be too much error in these distributions. And then once you have the log metalog representation, now if you represent that as density functions, of course every metalog has its density function representation, this is what you get. This is 1 log normal, this one here is 2, you go all the way up to 100. And even when you get to 100, there's still quite a bit of skewness left in this distribution. But I dare to say, before reading this paper, this is probably the first time anybody's ever seen what the density functions actually look like for sums of lognormals. Now the magic to this is in this quantile table, because what we've got is for each combination or variety of combinations of sigma, the shape parameter, and then the number of lognormals being summed, n, we have the corresponding set of 9 quantile parameters. And this again keeps the reference probability vector constant, which is fine. And I can get each of these quantile parameter vectors, each of these vectors, by simulating that particular cell. So for n equals 3 and sigma equals 0.04, that is the quantile vector of the sum of 3 identically distributed lognormal distributions. Now, this whole table, by the way, can be downloaded. We've now published a paper on this, of which Sam is a co-author. So this is a relatively stable table because we did it with 50 million simulations, right? It's not going to change much. In fact, it's accurate to all 3 significant figures here. But the next question you have is, well, you might very well have, well, wait a minute, I might have to redo that table, because what if I wanted, like n equals 13 isn't here. I've just got n equals 12 and n equals 14, right? Well, what if I wanted it for n equals 13? I'd have to redo the simulation. And the answer is no, you actually don't have to redo the simulation, because you can interpolate for in-between values. And that kind of interpolation is both feasible as a metalog and highly accurate. So what I mean by interpolation in a simple sense is if you wanted the quantile vector for n equals 13, you would just take the quantile vector for n equals 12, add that to the quantile vector for n equals 14, divide by 2, and now you have the interpolated quantile vector. Now the question is, next question is, how would you know that that's even feasible, right? Because remember, metalog distributions, you always have to check the feasibility. And there's a theorem in my 2011 paper, Quantile Parameterized Distributions, and it is directly applicable here. The theorem is that the set of feasible quantile parameters is convex. Okay, that's a very important theorem in this sense, because that means any convex combination of feasible quantile parameters is in fact feasible, and in this case you do not have to check the feasibility. So if you take, if you wanted for some sigma in between 52 and 62, let's say 57, and then something between 4 and 5, I don't know how you get 4.5, but whatever, you could take an interpolation of those 4, and assuming that the 4 of these are feasible, which you would check when you calculate the quantile table anyway, then you're guaranteed that the in-between values are feasible. So now you have a closed form representation of the sum of lognormal distributions that's a nice continuous function of sigma, for example, okay, and a nice smooth continuous function of n. See here, I only did n equals 60 and n equals 70. Well, what about n equals 65? You can put any number in there you want to and end up with a nice smooth lognormal distribution. So that's what gives you, and here I've got 4 different shape parameters. What does it look like? If you start off with something that looks fairly normal to begin with as a lognormal, then you end up with something that gets narrower. This is the average now. It gets narrower, and by the time you get to n equals 50, you've got something that's pretty close to being normal, like the central limit theorem. But if you start off with a lognormal like this one here that's quite skewed, then by the time you get to summing, this is 2 and 3 and so forth, by the time you get to summing 50, which is this one, you've still got quite a skewed distribution. And once again, this was fun working this out. So far as I know, it's the first time anybody's ever seen density functions for the sums of lognormals. We did publish a paper on this. It's in the IEEE. It's down here. The actual reference to it. It's freely available to anyone. You can download it from the metalogs.org website.